So I have to finish up chapter 16, the first 20 minutes or so of class. But then we're going to move on to chapter 17. But as I said before, the first part of chapter 17 is really just a continuation of 16. It's still all about acids and bases. Come on. Okay. That I'm not going to worry about because I did carry that over in today's lecture. So it's just this part I need. Okay, so we've talked about strong acids, strong bases, weak acids, weak bases. Well, for a base, nothing is strong except hydroxides. And the hydroxides are only strong when you have them attached to a strong enough metal, which is why group 1A and the bottom of group 2A work for bases. But acids are a lot more complicated. There are strong acids that are combined with a halogen. There are strong acids that are combined with a polyatomic. And there are weak acids that are combined with a halogen or with a polyatomic. So how do we determine whether an acid is strong or not? Well, we know that strength is measured by percent dissociation. If it dissociates 100%, then we consider it to be a strong acid. But what determines whether or not it will dissociate? What is it about these acids that allow them to dissociate 100%? As I said, bases can be strong or weak as well. These are our strong bases, just the hydroxides of group 1A or lower group 2A. So for acids, it's a matter of how easy does that H plus come off. The definition of the acid is it has to dissociate to give H plus in a solution. So how easily does that H plus break off? Well, there's a couple of things that determine the strength of the acid, but in general, the reason that they break off is because the bonds aren't that strong. A stronger bond will lead to less dissociation. So halogens, Cl, Bri, all make strong acids, but HF does not. HF is weak because HF has a very strong bond. It's a small molecule and highly polar. Fluorine is our most electronegative material on the chart. That combination of the polarity and the short bond gives it a much stronger bond. And you can see 562 versus the next one, which is all the way down at 431, and down to 299 for HI. Now, we consider HI, HBr, HCl all to be strong acids. But if we actually got down into it, the larger the molecule, the looser the bond is. So in general, HI is actually a stronger acid than HBr or HCl because that large size of the iodine means that bond is weaker. from last semester. The energy of the bond is Q1 times Q2 divided by D. D is the distance between the two nuclei. Q1 and Q2 are the charges. So all of these guys have charges of +1 and -1, but as D increases, the energy, because Q1, Q2 in the numerator doesn't change, as Q in the bottom gets bigger, the energy gets smaller. So even though we consider HCl, HBr, and HI all to be strong acids and dissociate 100%, they actually are not identical. So a short bond, a strong bond will lead to a weaker acid. And as I just said, the size of what's attached to the H plus makes a difference. The bigger anions have weaker bonds. Electronegativity makes a difference as well. So far we've got the strength of the bond, which can be determined if it's just hydrogen plus an anion by the size of the anion. But the electronegativity of the anion also makes a difference. Fluorine is more electronegative than chlorine is, which means that fluorine holds on to that hydrogen tighter. By the time we get to oxygen or nitrogen, we're not even in the acid anymore. So when it comes to polyatomics, we want to look at what is the central atom, how electronegative it is, and how many oxygens are attached. Because oxygen is the second most electronegative material on the periodic table, so it's going to pull. So when I look at something like that, not only is the oxygen the hydrogen is attached to pulling to make a polar bond, it's pulling all the way over to that oxygen. So electronegativity of the central atom and the number of oxygens we have will make a difference. Now here, in terms of just electronegativities, because they all have the same oxygens, adding more and more chlorines, which are highly electronegative, pulls the electrons, and it pulls the electrons all the way from here all the way over to there. So increasing the number of chlorines increases the pull on those electrons and makes it easier to pull off that hydrogen. So the more I can pull the electrons off the hydrogen in a polyatomic like this, the easier it's going to be to drop the hydrogen off, and the stronger the acid is going to be. And we can see that by the Kas here. With no chlorines, just plain old acetic acid vinegar we know is a weak acid. Its Ka is 1.8 times 10 to the minus 5. As I start adding chlorines, 1.4 times 10 to the minus 3, 4.5 times 10 to the minus 2 to 2.2 times 10 to the minus 1. Okay, so going back, I probably shouldn't have put the polyatomics in yet, but going back to just the electronegativities, increasing acid strength toward the right side of the periodic table as they get more electronegative, but increasing acid strength as they go down because the anions get larger. So like I said, I probably should have put, this probably should have gone there. Okay, so hang on. I don't want that there either. Okay, I guess I don't have another slide. So if we look at two of the strong acids, HClO and HClO4 and HClO3, they are strong, but HClO2 and HClO are weak. Because the more oxygens I have, the more that pull is going to be. I thought I had a slide in here that showed that. So if I just have that guy, I've got one oxygen pulling. As soon as I add 2 oxygens, I've doubled the strength. By the time I get to 3, I now have 3 oxygens as well as the chlorine pulling. Now the pull is so strong that the hydrogen comes off easily. And even more easier, is HClO4. So when I'm dealing with a polyatomic, I want to look at what is the central atom of the polyatomic. Is it electronegative? Are there other things that are electronegative attached to that? And how many of them are there? So if I go back to the previous slide, the carbon is not electronegative, but the chlorine is. And the more chlorines I add, the stronger the pull becomes. So I want to look at the electronegativity of the atom that OH is attached to, and any other electronegative elements that are there. And the more electronegative elements that are there, the stronger the pull of the electrons, and the stronger the acid becomes because the hydrogen comes off more easily. So more oxygens here. Chlorine is already electronegative. It is pulling here. But oxygen is also electronegative. So add more and more and more oxygens. We're adding more electronegativity. We're increasing the pull of the electrons we have on the hydrogen, and the hydrogen comes off more readily. Now, if I'm looking at a mixture of things, the weakest one here is going to be the one that doesn't have a halogen attached, because the only thing pulling on those are the oxygens. So this one's going to be the weakest. Now, B only has one halogen attached. So that's pulling, yes, but it's not pulling as strong. So from weakest to strongest, that's number 1. That one would be number 2. But then A and D both have 3 halogens attached. So how do I decide which one is stronger and which one is weaker? Well, now I go back to the electronegativities. And fluorine has a higher electronegativity than chlorine does, so it'll pull harder. So number 3 becomes the one with the 3 chlorines on it. And 4 becomes the one with the 3 fluorines. So we're looking at the electronegativity of the material and how many electronegative things there are. And if we're dealing with just hydrogen and an element, not a polyatomic, we just want to know how strong the bond is. And that depends on the size of the anion, which is why HI falls apart easier than HF does. Okay, how many ionizable hydrogen atoms does the following have? Well, it's not going to have a hydrogen come off that is directly attached to the central atom. It has to come off in OH. So for A is standard phosphoric acid. All of these guys come off, and it has 3 ionizable atoms. B is phosphorus acid. It's missing 1 oxygen. I don't know if you guys remember from last semester, but IC versus OUS tells you how many oxygens are there. So phosphoric has more oxygens than phosphorus, but we lost an oxygen, so now we only have 2 ionizable. And the next one, even though we've stuck extra things together, It's still those two guys that ionize. So look when you're ionizing with a polyatomic for the H's that are stuck on the oxygens. We don't want other hydrogens coming off. We just want the ones that are on the oxygens because the oxygens are electronegative enough to pull those guys off. Okay, so we did A up above already. B, I've got 2 again. C, I've just got the 1. Oh, wait a minute. We didn't do that one up above. Okay. So 1, 2, and 1. Just the hydrogens that are on the oxygens. I was looking at A and thinking we'd done it up above, and we didn't. That is hypophosphorus acid. H2SO2 is hyposulfurous acid. And the last one, I don't even know what the name is. Okay, so when we're looking at acid strength, look for if it's attached to just an element, what is the electronegativity of the element? And if it's in a polyatomic, how many oxygens, how many other electronegative elements are there? Now, I said that when I introduced acids that there was a third type of acid, Lewis acids and bases. We're going to start looking at these in the end of chapter 17. These are defined by lone pairs. A Lewis acid is anything that can attach itself to a lone pair, which is why H plus is an acid. H plus doesn't have any electrons. It attaches itself to a lone pair, and things like water to make H3O plus or ammonia to make NH4 plus. A Lewis base is anything that has a lone pair. Difference between Lewis acids and other types of acids is the reaction of these is not a dissociation. They don't break things off. They attach things on. So our strength is not determined by does a hydrogen break off, it's determined by what can add on. It's a synthesis reaction. So a Lewis acid plus a Lewis base, the Lewis acid has an empty orbital, Lewis base has a lone pair, makes what we refer to as a Lewis adduct. Adduct just means adding them. We're just bonding those two things together. So in this case, when I have ammonia, ammonia is a base because it's got a lone pair. Hydrogen attaches to it. So hydrogen would be a Lewis acid, ammonia would be a Lewis base, and I create the conjugate acid HNO4+. But notice, nothing's falling off here. I'm adding something to it. If I just put ammonia in water, ammonia gets an H+, yes, but it pulls it off of water. Water loses its hydrogen. So there is a dissociation happening there. Water is going to H+ and OH-. Here, there's no dissociation present. It's just an acid plus a base. We get this conjugate adduct. Now, I don't know how many of you got introduced to this term because I think I'm the only one who introduces it in 1127. America, for some reason, does not introduce this concept, but every place else in the world they introduce it. It's a covalent bond. But most covalent bonds are created from an orbital that has one electron and an orbital that has another electron. You bond them together, you get 2 electrons. A coordinate covalent bond, when it's created, looks exactly like any other covalent bond. I cannot distinguish between those 4 NH bonds. But it's created from an empty orbital and one with a lone pair. So it's not bringing 2 things together that each have an electron, but it's bringing something together that has a lone pair and something that has an empty orbital. So that's all a coordinate covalent bond is. It's just a regular covalent bond. Like I said, I can't distinguish between those NH bonds, but it's created in a slightly different way. Most common Lewis acid base found in nature is this guy. Boron has an incomplete octet. It only has 3 electrons. There is no way for it to make a full octet. So, boron trifluoride has an empty p orbital still. Ammonia has a lone pair. In nature, that is how boron trifluoride is found. It is found attached to a nitrogen because that is the only way boron can complete its octet. So boron becomes a Lewis acid, ammonia is a Lewis base, and I create a Lewis adduct. NH3 simply attaches to that empty p orbital. Now, if I put other things on the boron besides fluorine, it's going to have the exact same situation as any other acid. The bigger the halogen, the easier it is to do something with it. Break off the hydrogen. In this case, the iodine is big, it's bulky, but it's pulling those electrons in, and it allows a better chance of it attracting. So same pattern, the bigger it is for a halogen, the stronger the acid becomes. Now, the reason we're going to see this is because we're going to start seeing these in the end of chapter 17 when we talk about solubilities of transition metals. This is very common in transition metals or aluminum and some of what we refer to as the post-transition metals, things below aluminum, tin, lead, antimony, bismuth. They have d orbitals. And when I start making ions out of them, I can leave some of those d orbitals empty. And leaving those d orbitals empty then allows something that has a lone pair to attach. When I put something like aluminum chloride into water, it automatically does this. It starts pulling water in and bonding to the water. It stabilizes that aluminum. But someplace in here, there are also 3 Cl minuses. So we're going to be looking at this a lot when we talk about solubility in chapter 17. Main things that we can find doing this: aluminum, iron 3, chromium 3, copper 2, zinc, cadmium. There are others, but what we're looking for is something that has empty orbitals that we can attach to. Now, you can see aluminum is attached to 6 hydrogens, or 6 waters. There are only 5 d orbitals. So accept the fact that 6 is normal. It's just like we did hybridization with the S&Ps to get CH4 in a tetrahedral shape. There is some hybridization going on, but the standard is 6 things attached, even though there are only 5 d orbitals. Okay, compounds with double bonds actually turn out to be Lewis acids and bases because they can do this. They can move one of their electrons pairs over to the oxygen, leaving an empty orbital, and then attach to things. So water can attach to that empty orbital. Carbon dioxide, we wouldn't think of acting like an acid or a base, but it does. This is how we end up with acidic water. I said hydrogen or water plus carbon dioxide makes H2CO3, which is an acid. This is how it does it. This is now H2CO3. Okay, so the only other thing that was in chapter 16, I've actually moved into the chapter 17 PowerPoint. So we're starting chapter 17, but as I said, it really is just a continuation of chapter 16. Okay. So we're going to start with the concept of a common ion effect. The common ion effect adjusts the equilibrium of my situation because I now have a product. There is already a product present. So here I have lead chromate attempting to dissolve, but if I add more chromate from another source, you can see I'm starting to form more lead chromate. It's gathering on the surface up there. The addition of one of the products, according to Le Chatelier's, shifts my equilibrium backwards. And that will be true not just in this common ion effect, which we get to tomorrow probably. I'm not sure. No, Monday. But also with acids and bases. The equilibrium of an acid or a base can be manipulated by externally changing the pH. If it's dissociating, I have H plus, some anion, or I have OH minus and some cation. By changing the OH minus or the H plus concentration, I can affect the situation of my equilibrium. So I have a 0.3 molar solution of, this is nitrous acid. Its Ka is 5.6 times 10 to the minus 4. What's the pH? Well, I'm going to check to see if I can drop the X. It's not over 1,000, but it's 500 and something, so I'm going to go ahead and say, let's drop it and we can check later. So if I can do that, then my Ka is simply equal to X squared over the initial concentration. So that is standard if I can drop the X. That Ka just becomes equal to X squared over the initial concentration. So 5.6 times 10 to the minus 4 equals X squared divided by 0.3. X squared is equal to 5.6 times 10 to the minus 4 times 0.3, or 1.7 times 10 to the minus 4. X then becomes 0.013. I double checked. 0.013, my X divided by my initial concentration times 100 is 4.3%. So it was okay to drop the X. So now I can use that X and find the pH. So a 0.3 molar solution of nitrous acid has a pH of 1.89. It's pretty acidic. But I make this not in pure water, but in a solution that has some NO2 minus in it. I'm going to put in some salt, sodium nitrite. It's telling me I put in 0.2 moles of that. I still have that 0.3 moles of the nitrous acid. Notice it does give me moles, but it's all in 1 liter, so I just transferred it into molarity. Ka is still 5.6 times 10 to the minus 4. So I'm still going to drop the X because it worked out the last time. But now my icebox looks like this. I have product in there. It's still going to go forward because I still have to dissociate that acid and give me H+. It's still going to go forward. But now my Ka of 5.6 times 10 to the minus 4 is equal to 0.2x divided by 0.3. I put in that value instead of a second x. Now, when I do this, my x previously was 1.3 times 10 to the minus 2. My x value now is all the way down to 8.4 times 10 to the minus 4. The presence of one of the products, Le Chatelier says, shifts it back to the reactants, and therefore the acid dissociates less. There's more in the molecular form still than there is H+, and my x value went way down. If my x value goes way down, then my pH goes way up. And my pH went up from 1.89 to 3.06. This is the common ion effect. Adding a common ion, adding the anion of the acid as a salt gives me extra product. And that extra product, Le Chatelier says, shifts back to the reactants and lowers the dissociation I have. The acid is weaker and my pH goes higher. So the common ion effect reduces dissociation and raises my pH. Now, this works for other things, but we're focused on acids and bases right now. When we get into the rest of chapter 17, we look at solubilities, common ion will have the same thing. It will reduce dissociation. But for now, we want to know that it reduces dissociation and raises the pH. So calculate the pH of a solution that is made from 0.16 moles of hydrozoic acid. Hydrozoic acid is a very strange thing because we've just put 3 nitrogens together and stuck 1 hydrogen on them, as opposed to 1 nitrogen and 3 hydrogens. And I'm going to put in 0.19 moles of sodium azide. Now, you probably have never heard of any of these things, but think about what it must be like to put 3 nitrogens together that have to make 3 bonds. It makes this guy very strongly bonded until you ignite it. Then it blows up. Gives you a lot of energy out. Guess where you find sodium azide? Sodium azide is in your airbags in your car. As a solid, as long as nothing happens to it, it's fine, but there's a little trigger in there. There's a piece of gold and an electrical trigger that if for some reason you are in an accident and it hits the correct thing and it ignites that sodium azide, it releases a lot of nitrogen gas and it fills your airbag. Again, nothing that has to do with this, it's just you should know that there's chemistry every day. Okay, the Ka of hydrozoic acid is 2.5 times 10 to the minus 5. So my icebox looks like this: 0.16, 0, and 0.19. So 0.16 divided by 2.5 times 10 to the minus 5 is 6,400, so I'm good for dropping the x. So again, K is just equal to x squared over my initial concentration, or 0.19x over my initial concentration. So 2.5 times 10 to the minus 5 becomes 0.919x divided by 0.16. And x becomes 2.11 times 10 to the minus 5. Okay, that's the wrong, it was okay to drop the x. That doesn't need to be there. That's left over from the previous slide. So my pH is 4.68. Well, what would my pH look like if there was no sodium azide in there? Well, 2.5 times 10 to the minus 5 would simply equal x squared over 0.16. X squared would equal 4.0 times 10 to the minus 6. X would be equal to, I think I can do this in my head, but I'm going to, yeah. In my head, I said, well, take the square root of 4 and take the square root of negative 6, but I just wanted to make sure I was doing okay. So it's 2.0 times 10 to the minus 3, and the pH of that would be 2.7. So just this guy, the pH is 2.7. So you can see the presence of that salt lowers my dissociation and raises my pH. Now, why do we care? We're going to use the common ion effect to create buffers. I found this yesterday when I was online. Very acidic acid, very acidic base, buffer. I'm here to keep the balance. That's what a buffer does. A buffer balances your pH. The definition of a buffer is a solution that will resist change in the H plus concentration when small amounts of acid or base are added. Now, it's not going to work if I take 1 mole of acid and I dump in 3 moles of a base. But if I have 1 mole of acid and I dump in, say, 0.1 mole of base, the buffer should maintain pretty close to the original pH. This is what a buffer does for us. This is two solutions, one of just plain water, the other one of a pH 8 buffer. And it's got an indicator in it. When I add a little bit of acid to it, that indicator goes completely red, indicating that it went totally acidic. But the pH 8 buffer stays yellow, which is the point. We want that pH to stay as close as the original as possible. That is the purpose of the buffer. So how do we do that? We use the common ion effect, and we make the buffer from a weak acid and its conjugate base. So something like the nitrous acid and sodium nitrite, or the hydrozoic acid and the sodium azide. I could also do it the other way around. If I want a basic buffer, I could make it from a weak base and its conjugate acid. I could make it from something like ammonia and ammonium chloride, which would add the NH4+. But the idea is I want to have both sides, both of the conjugates, because I want to be able to shift back and forth as I add acid or base. So, can I make a buffer from HF and NaF? Sure, that's a weak acid and it's salt. I can make a buffer out of that. Can I make a buffer out of methylamide and the methyl ammonium ion? Sure, that would give me a basic buffer. The weak base and its conjugate acid will make the buffer. But HI, starting off, without even looking at what it's attached to, HI is a strong acid. Strong acids and strong bases are not going to make buffers because they're not reversible reactions. The buffer relies on Le Chatelier's principle, and that only works if you have a reversible reaction. So HI will never make a buffer, and it's not added with the salt anyway. It's added to I2, which is the element. So even if I took a weaker acid like HF, HF and F2 is not going to make a buffer because that's not the conjugate. So how does all of this work? Okay, suppose I have that ammonia and the ammonium ion. If I add acid to it, that acid is going to neutralize that OH minus. As it neutralizes that OH minus, it removes it from solution. And Le Chatelier's says the equilibrium will shift to fill that hole and will shift to the right. I now will create a new equilibrium, but I still have, as long as I haven't added too much H+, I still have both B and BH+ in solution. So I still have a buffer. I can't add enough acid that it completely removes everything, but as long as I add a small amount of acid, I just maintain both B and BH+, and I maintain an equilibrium. But HClO4 and its conjugate base, ClO4, you cannot do this with a strong acid. You can't do this with a strong base because they do not have reversible reactions. And we need something that will shift forward or backward as I mess with the H+. So let's look at what happens when I start adding little bits of H or OH. So I'm going to use just a generic HA and A-. In this case, I chose to go back to the nitrous acid and sodium nitrite. So when we did this previously, we found that the pH of this is 3.06. But I'm going to add 1 ml of a 1 molar solution of hydrochloric acid to 100 mL of that solution. Now, if I'm going to add acid or base, I want to add a strong one. because I want to add either H plus or OH minus, not just a generic acid or base. I want to add straight the H plus or the OH minus. So I'm going to add HCl. That will give me 1 mil of a 1 molar solution of H plus. So I'm adding more of that H plus. That H plus is going to start reacting, whoops, with the NO2. That's supposed to be NO2, not NO3. So that's going to start reacting with the NO2 minus, and it's going to start shifting things back to the left. So Le Chatelier's, if I increase one of the products, it removes the other product and creates more of the reactant. Now, when I add HCl, I'm going to make the assumption that because it's a strong acid, it's going to completely react with the base. When I am done, that H plus is now all HNO3. And I'm back to 0 H plus. So, oops. So I'm going to reduce the amount of, I guess I wasn't paying much attention when I did this yesterday. I'm okay when I get to there. Okay, so it reduces the amount of the nitrite ion, NO2 minus. It increases the amount of HNO2, and the H plus concentration is going to completely react with the NO2, and how much it decreases the NO2 by and how much it increases the HNO2 by is going to be determined by how much of the acid I added. So I'm going to create a brand new equilibrium. I'm going to determine how much of the NO2 disappears, how much of the HNO2 appears. All of the H plus is gone now, and I'm going to create a new icebox. But to do this, I can't just add 1 mil of 1 molar. I have to actually know how many moles of things I have. So I determine the number of moles of NO2 minus by taking the 0.2 molar times, I'm doing 100 milliliters, so 0.1 liter, and I did the same for the HNO2. So I have 0.02 moles of NO2 and 0.030 moles of HNO2. How much H plus did I add? Well, 1 molar times 0.001 liter is 0.0001 0.001 moles of HCl, which is 0.001 moles of H plus. Now, I'm going to add that number of moles of H plus to the HNO2 and subtract it from the NO2. So 0.001 moles of H plus react with 0.020 moles of NO2 to reduce the NO2 minus by that much and increase the HNO2 by that much. So my new value for HNO2, what the hell was I thinking here? I'm supposed to subtract it from that and add it to that. I thought I fixed all of this. I was working on this yesterday and I noticed that it was a mistake, and I thought I fixed it. Sorry, guys. I was sure I fixed all of this. But notice, I'm now going to take those number of moles, and I'm going to divide it by the volume, which is no longer 100 milliliters. My volume is now 101 milliliters. So I have to take that into account when I calculate my new molarity. My new molarity here is 188. My new molarity there is 307. Seriously, guys, I thought I fixed all of this yesterday afternoon. So I've removed some of the NO2. I've added to the HNO2. And I'm going to start setting up a new icebox. Big important thing, the biggest thing students forget to do in this thing is to take into account the new volume. The new volume has to be included. You take the molarity and the volume you have of your acid and your salt, find the number of moles. Adjust those with the moles of acid you added, but then to get the new molarity, make sure you use the new volume. I don't know who's texting me, but you gotta stop it. So this is actually 188, and this is 307. .1 times 10 to the minus 4. Three point 3.04. So my original pH was 3.06. Adding acid should lower my pH, which it does. It lowers it to 3.04. But it didn't change it by much. Adding that 1 ml of acid changed my pH by 0.02. This is the purpose of a buffer. Adding that HCl, if I added that HCl, if I added a 1 molar solution of HCl to water, I'd be down in pH 1 or 2. By adding it to something that already has both sides present, I barely changed the pH. Now, I could do the same thing by adding a strong base. Now I get the opposite effect. So what I'd actually done in all of those previous things that I had done, where all the numbers were wrong, I had basically done this. Because now, adding the base will neutralize that H plus and remove it. Now, Le Chatelier says it's going to shift it to the right. Now, I would do exactly the same thing. I would take 1 molar OH minus times 1 milliliter. I would do 100 milliliters of the hold on a second. I would do 100 milliliters of the total solution. So okay, so I don't need that, and I don't need that. All I needed was my ice boxes. So if I add NaOH to it, I know what I did wrong yesterday. I started doing it as a basic thing, and I said, no, let's do it as an acid, and I apparently didn't change enough things. So adding NaOH is going to neutralize that H+. It's going to shift things to the right, which will increase NO2, decrease HNO2. And again, we're simply going to create a new icebox. So this was the correct thing to do. I'm adding to the NO2, I'm removing from the HNO2. This is correct for adding OH minus. Okay, so these were the volumes that I had, 0.101 liters again, new values, removing or adding the amount I've added, and new things in the icebox. And I've added base, so my pH should go up from 3.06, and my pH went up to 3.11. A little bit bigger of a difference than adding the acid was, but it's still, they both round to 3.1. Not that big a difference. So I apologize. Everything that I had up there to start with was the base stuff, but the acid is now up there, and this is the base. So the purpose of a buffer is to have a certain balance in equilibrium of HA and A minus. And if I add acid, it shifts to the left, gives me a new equilibrium with more HA and A minus, but I get an equilibrium. If I add base, it shifts it to the right, reducing my HA and increasing my A minus, but again, then I get a new equilibrium. And that equilibrium should not be that different from my original one. That is the whole purpose of a buffer. So it says it works with a basic buffer. Of course it does. Why would it make a difference if it was a base or an acid? Because in both cases, we have conjugates. As long as I have two conjugates, it's going to do exactly the same thing. It's just I'm going to have the conjugate and OH minus versus the conjugate and H plus. But adding acid would react with that OH minus. Adding base would increase my OH minus, and each way would shift my equilibrium. This isn't as good a chemistry cat as some of them. A buffer is a VAM pH slayer. Not as good as some of the other chemistry cats. So, how do we get... No, let's take a 5-minute break before I get into this. Because so we've seen how a buffer works. I have a buffer whose original pH was 3.04. When I added acid, it dropped to 3.06, it dropped to 3.04. And when I added base, it went up to 3.11. But what about finding a buffer for a certain pH? That nitrous acid, sodium nitrite will work if I want a buffer at 3. But suppose I want a buffer at a different pH. We saw the picture of the buffer at 8. What is the pH of a buffer? Well, we did it with ice boxes. Let's find a cheat so we don't have to do an ice box. Ka is H plus times A minus over HA. If I take the negative log of both sides and I rearranged it, it says that pH is equal to pKa minus the log of the acid over the base concentrations. Or, flipping base over acid, pH is equal to the pKa plus the log of A minus over HA. That means the pH of a buffer is going to be determined by, 1, what is the Ka of the buffer, and 2, what is the concentration of the acid versus the concentration of the base. This is known as the Henderson-Hasselbalch equation. It's just the same thing as Ka equals H plus times A minus over HA. I've just rearranged it to get an idea of where the pH of a buffer would be. And it would be somewhere in the neighborhood of the pKa. Now, Henderson-Hasselbalch has to work when we have both base and acid in there. Because if one of those things is missing, I can't do a log. Now, interesting thing. We use molarity every single time we do an icebox. I don't have to use molarity here because it would be molarity over molarity, and the volumes would cancel out because they're both in the same solution. So if it gives me moles instead of molarity, in Henderson-Hasselbalch, I can use moles directly. I don't have to find the molarities. Now, it does only work under certain circumstances. It has to be a common ion effect. It has to be having both HA and A minus, or B and BH plus, and the Ka cannot be too large. If the Ka and the concentrations are too close together, and we couldn't drop that X when we did our calculations, it's not going to work. So it only works when K is very small, so that we can use the initial concentration of the acid or base as my denominator. So if I tried to use hypochlorous acid, which is 1.1 times 10 to the minus 2, and I had a 0.01 molar hypochlorous acid and a 0.012 molar hypochlorite ion, that's not going to work. It's not going to work because my Ka is way too close to my concentrations. I need a low Ka and higher concentrations. I need the situations where we could drop the X in our icebox to use the Henderson-Hasselbalch. So, cyanic acid and cyanate ion. we make a buffer. Now, this will make a buffer. I'm not sure I would recommend making a buffer with cyanide, but what the heck. I have 0.125 molar cyanic acid and 0.160 molar of the cyanate ion. So my pKa, if my Ka is 3.5 times 10 to the fourth, my pKa is 3.46. Okay, that was, I should have had a note in there someplace. Notice this says -4. That's a typo here. That should be -4. If I had a +4 there, I would not have a reasonable pKa. I'd be up in the thousands. That was a typo in the book. So the pKa is 3.46. My pH equals pKa plus the log of the base over the acid. So it's 3.46 plus the log of 0.160, which is my cyanate ion, over 0.125, which is the molarity of my cyanic acid. And my pH is 3.57. A lot easier than doing an icebox, right? Yeah. Henderson-Hasselbalch is a really nice way to avoid having to do the iceboxes. Now I have formic acid. Okay, I think we all know what cyanide is, right? Seen too many spy movies and stuff. Any idea what formic acid is? Anybody know what a formicary is? Formicary is an ant farm. Formic acid is the stuff that red ants have that stings when they inject you. When they inject you, it's not some sort of poison or anything. It's just a straight acid. It's why it burns so bad. Again, nothing to do with this problem. You should just learn some things that are outside of these problems. So 1.8 times 10 to the -4, my pKa is 3.74. I'm going to put in 0.17 molar formic acid and 0.120 molar sodium formate. So for A, my pH is 3.74 plus the log of base over acid, so 0.120 over 0.170, becomes 3.74 minus 0.15, and my pH goes down to 3.59. If I have 0.1 molar formic acid and 0.15 molar sodium formate, then my pH becomes 3.74 plus the log of, okay, I did this on purpose. I know it says 0.1 and 0.15, but I put the same numbers in, I just swapped them because I wanted you to see something. So that is why it doesn't say 0.15 and 0.1. I've flipped the numbers. Now, instead of subtracting that 0.15, I get the same log, but it's positive. So now my pH goes up by that 0.15. And like I said, I did this on purpose. This is not just another mistake. I did this on purpose so you could see how the ratios of acids and bases will either increase your pH or decrease your pH. In general, I can assume that if I have more acid or more base than acid, my pH is going to go up. So I had more base than acid in B, and my pH went up. It became more basic. If I have more acid than base, it's going to become more acidic, and my pH is going to go down. So when I had more acid than base, my pH went down. With the exact same concentrations, just flipping the acid and the base, I just changed from a negative log to a positive log. And it either goes down because I have more acid, or it goes up because I have more base. So in general, if I have equal amounts of acid and base, then that just becomes 1. And then the log of 1 is 0. But any other ratio, more acid makes it more acidic, more base makes it more basic. Okay. Buffering ability. Buffering ability is how well does it work as a buffer? I have a solution that contains the Okay, now this is interesting because I have H3PO4 that goes to H2PO4 minus to HPO4 minus 2 to PO4 minus 3. I use the book uses the two center ones here. So I have the dihydrogen phosphate ion and the hydrogen phosphate ion here. The Ka of the dihydrogen phosphate is 6.32 times 10 to the minus 8. Because when I'm doing this, the one with more hydrogens is the acid. So what is the pH of a buffer solution that contains 0.25 molar acid and 0.20 molar base? So the pKa, 6.32 times 10 to the minus 8, becomes 7.20. So the pH becomes 7.2 plus the log of 0.2 over 0.25. Now I have more acid than I have base, so my pH should be going down, and it goes down to 7.1. Isn't this so much better than doing an icebox? Anderson-Hasselbalch is so great. And because all the problems that you're going to get are going to be ones where you don't have to do a quadratic, you're never going to have a situation where you have acid and base together where you can't use the Henderson-Hasselbalch. Because if we couldn't use the Henderson-Hasselbalch, it would mean we couldn't drop the X, and then you'd end up with a quadratic in your icebox. You're never going to have that situation, not on a test. So as long as you have an acid and a base, you can always use Henderson-Hasselbalch. Now, what is the pH after I've added 50 milliliters of 0.5 molar KOH? I'm adding that to 500 milliliters of the buffer. So I had a 0.25 molar concentration of acid, multiply that by 0.5 liters. That's how many moles of acid I have. Then I figure out the moles of base. So moles of material you have is just concentration times volume. Just make sure your volume is in liters. Then I figure out how much OH minus I add. So 0.5 molar times 50 milliliters is 0.0250 moles of KOH, which is 0.0250 moles of OH minus. This is exactly the same thing that we were doing previously. Find the moles of your original materials, find the moles of what you're adding, and add or subtract as necessary. So if I'm adding OH minus, it's going to remove that guy and therefore shift things forward, so I should get more base and less acid. So decrease the acid, increase the base. So 0.125 moles of acid minus 0.025 is 0.1 mole of acid. 0.1 plus 0.025 is 0.125 moles of base. Now, I went ahead and did this and calculated a new molarity. But I told you don't even actually have to do that. I could have just gone ahead and done that pH is equal to pKa plus the log of 0.125 over 0.1. I didn't necessarily have to change the volume because volume is the same for both of them. I divided both of them by 0.55 liters. Those are going to cancel out. So I could have taken the straight moles here, but I went ahead and calculated the molarities. And then the pH would be the log of the base over the acid. I'm adding OH minus. I want my pH to go up. And now my pH has gone up from 7.2 to 7.3. So I did get an increase without adding anything. My pH was 7.1. By adding base, I did go up to 7.3, but that's not awful. But that is the buffering capability of this combination. What would happen if I added that same amount of KOH to pure water? Now, I'm going to put 50 milliliters of 0.50 molar KOH to 500 milliliters of pure water. I'm going to have 0.0250 moles of KOH, which is the same amount of moles of OH minus. I now have a 0.050 molar OH minus concentration. Calculate a POH of 1.3, and my pH is 12.7. The buffering ability for that system kept my pH within 0.2. If I didn't have that buffer there, adding that amount of KOH would have jumped my pH all the way from 7 to 12.7. That's the purpose of the buffer. If I just use pure water, this is what happens. So I want to make a buffer, and I need it at a certain pH. How do I do it? Well, I know the pH is related to the pKa. Then I know it's related to the base over the acid. If I want to make a buffer, I have to figure out what I need for a ratio of base to acid, as well as knowing what the Ka is. So, how much acetate ion and how much acetic acid would I need to make a buffer solution of pH of 4? Ka is 1.8 times 10 to the minus 5. pKa is 4.74. Again, 1.8 times 10 to the minus 5 is one of the only Ks I have in my head, and I know that the pK of that is 4.74. So 4 equals 4.74 plus the log of the base over the acid. So 4 minus 4.74 is minus 0.74. That equals the log of the base over the acid. This is a regular log, not a natural log. So to get rid of it, I take 10 to the value, and I get 0.182. So I need to make a solution that is 0.182% of the quantity of base I have. So 18.2% acid versus 100% base. I don't have a great ratio there. 0.182 acid versus 1 base is not a really good balance, but it's how I get that pKa down to 4. And it will work. But it doesn't tell me exactly how much to put in. It just tells me whatever I put in. If I put 1 milliliter of base in, I need 0.182 milliliters of acid. If I put 10 milliliters of base in, I need 1.82 milliliters of acid. It's not telling me exactly how much to do. It's just telling me what the ratio has to be. So if the ratio is going to stay the same, if I have a choice between 5 and 3 versus 0.05 and 0.03, the ratio is still 0.6, I'm going to choose the guy with the higher concentration. Because the higher concentration means I have more stuff in there. More stuff in there gives me a better chance of balancing my equilibrium. Remember, this only works if I can drop the X. I don't want my concentrations getting so low that I can't drop that X in my icebox. So if I'm given a choice and I'm told that's the ratio I have to have, take the one with the higher concentrations. It makes a better buffer. Okay, buffering capacity. Buffering ability is how does it compare to pure water? Buffering capacity is how much acid or base you can add before it messes things up. Normally, it's within 1 pH unit of the Ka, the pKa. So, like I said, buffering ability is how does it compare to pure water? Buffering capacity is how much can you add before you mess things up. So, best pH, equal amounts of base and acid, where the pH is equal to pKa. That gives me the best buffering capability, the best buffering capacity. So when I'm saying capacity usually within 1 pH unit, that's 1 pH unit of pKa. My best situation is when the pH is exactly equal to the pKa. Can't always do that. I can't always find a Ka that matches the pH that I want. So if you can't be exact, find a pH that's as close to the pKa as you can, plus or minus that 1 unit. So if I have acetic acid and my pKa is 4.74, I could technically go down to 3.74 or up to 5.74 and be okay. If I go down below 3.74, I've got too much acid. If I go above 5.74, I've got too much base. And I'm not able to use that as a buffer. So I want a buffering solution of pH 5.5. Well, I know that ten to the minus 10 is not going to work. So I just did acetic acid. I know that my pKa is usually 1 less before the decimal point of what that exponent is. So with an exponent of -5, I expect my Ka to be 4 point something. And we just did it, and it was 4.74. All of these guys that have -4s are going to be 3 point something. That's 3.77. So the first thing I want to look for is one where the exponent is preferably 1 greater than what I want. Preferably, I'd like something with 10 to the minus 6. If I want a 5.5 pH, I want something with a 10 to the minus 6. It's not giving me that. If I can't find one that's 10 to the minus 6, I'm going to go for one that's 10 to the minus 5 or 10 to the minus 7. Is that making sense? Okay, so I want the exponent I want the exponent to be possibly 1 greater than the pH. Negative of that. So like I said, if I want 5.5, my best shot would be something that was 10 to the minus 6. Since I don't have that, I go either 1 less, 10 to the minus 5, or 1 more, 10 to the minus 7. That keeps me within that +1, -1 pH range. So from this table, the best thing I can use for 5.5 is the acetic acid buffer. I would simply have to add more acetate ion to increase the pH. I want a buffer solution at 10.8, but it wants a weak acid. It's not telling me to find a base, it's telling me to find a weak acid. At 10.8, I'm going to look at those guys. Preferably, I'd like something 10 to the minus 11. I don't have anything, but I do have things that go down 1, 10 to the minus 10. So the log of 5.8 times 10 to the minus 10 is 9.24. That's a 4. The log of 1.1 times 10 to the minus 10 is 9.96. Now, if I want to stay within that plus or minus, it has to be between 9.8 and 11.8, which means that boric acid is too low. So my choice will be phenol. So my buffering capacity is the amount of acid or base that I can have added and still maintain the pH, and be aware that you can blow the buffer. If you add too much H plus or too much OH minus, you can go beyond the buffering capacity. and you can do what we call blowing the buffer. And all of a sudden it becomes an acid solution or a base solution. And I've got like 2 minutes left in class. The next stuff is not on a test or anything, it's just another why do we care. Most important reason we care is living systems. Our body is filled with buffers. Our blood has to be maintained between 7.35 and 7.45 for the enzymes to properly function. If I have too much OH minus, I get something called alkalosis. If I have too much acid, I get something called acidosis. And if I get too far away from that 7.35 to 7.45, I will literally die. Because enzymes are protein chains. They contain an amino group that acts as a base and picks up an H+, and an acid group that loses its H+. And when they both do that, biologists call that a salt bridge. We call it an ionic bond. The NH4+ bonds to the COO-, and it keeps that shape of the enzyme. If I go too high a pH, then I lose the H+ off the NH3+. If I go too low a pH, I add H to the CH2COO. And either way, I break that ionic bond. So buffers are extremely important in lab when we want to do an experiment, but they're also extremely important in everyday life. We've talked a little bit about some things that can be used as buffers. One of the main buffers in your body is carbonic acid, CO2 that you breathe, water in your blood, and your kidneys produce bicarbonate. Another one is the phosphate ions. So this last part is just another one of those. You should know where these things apply in real life. But up to where it says this is how you find a good pH is tested. And then tomorrow, we're going to look at a little bit more of acids and bases and talk about neutralization.